Let me briefly introduce you, and then I will give it away for you. So today we will have a talk by Viktor Bengs, who is a postdoc at LMU Munich and focuses on uncertainty quantification in deep learning, bandits, and explainable AI. And today he will talk about his recent NeurIPS paper, which he presented last year at NeurIPS. So without further ado, please take it away, Viktor.
Yeah, thank you very much for the kind introduction. So, yes, I will present here the NeurIPS paper, Pitfalls of Epistemic Uncertainty Quantification through Loss Minimization is the title. So it's a joint work together with Eyke Hüllermeier from the LMU as well, and Willem Wageman from Ghent University in Belgium. All right, so what are we looking at? So we are looking, so I won't introduce the standard notation of machine learning. I guess everyone is familiar with that. X is a feature space, Y is a label space. Label space in our setting here will be classification, so it consists of k-many labels. All right, and what machine learning people are interested in, for now a while, and now it has become a very hot topic, I would say, is representing uncertainty of a learner in a specific way. And what can be done is one can distinguish these uncertainty representation or their awareness of the learner regarding three levels. So I like to decompose it into three levels regarding the statistical uncertainty awareness, more or less. Yeah, so what is the very first level, or the level 0 rather? It's when you have a learner who is predicting simply a hard label. Yeah, so your mapping is simply mapping features to labels. So these are your hypotheses. So if we are in a free class label setting with three classes, y1, y2, y3, you would predict, or your learner rather, would predict one of these three corners of the simplex. So quite simple example, what could be the case. So imagine you want to predict, so since this is a reading course organized by the TUM and ETH Zurich, you want to predict the outcome of a soccer game between the FC Zurich, I guess is the team in Zurich, and Bayern Munich. So there are three possible outcomes: Bayern wins, it's a Zurich wins, or a draw. So these are the three outcomes you want to predict. And well, this is one way to predict, and this prediction, or rather the hypothesis itself, does not report any uncertainty. So you just predict a hard label and that's it. There's nothing like uncertainty awareness involved. And now what you could do is you could, instead of predicting a hard label, you could introduce the first level of uncertainty in the sense of a probabilistic forecast, more or less, or a probabilistic prediction, where you now predict for a given instance X, now a probability distribution over the labels. So now in our free class label setting again, we predict not a corner of this triangle here, which is, by the way, a 2-simplex, of course. So the 2-simplex representing every possible probability distribution for three classes. Instead of a corner point, you could predict something within the triangle. So the closer it is to a corner point, the more it resembles the point mass distribution on the corresponding class. So the closer I am with this point here to this corner, the more my prediction resembles the entire probability for class Y1. The more I'm in the middle, so to speak, the more it resembles the uniform distribution over all three classes. And you can imagine that with this you have now a possibility to represent uncertainty in a way, yeah. So in the sense of a probabilistic uncertainty representation. And well, there are also learning algorithms which are doing this, yeah. So softmax regression, naive Bayes, you name it. And what is a quite recent movement, I would say, in this entire picture is the case of making level 2 predictions, where you now go even one level above, yeah, where your predictions are now going from one instance to a probability distribution over probability distribution of the labels. Yeah, so what you have here is you don't predict just a single point in the simplex, going back to our free class example, you rather predict an entire probability distribution over the simplex. Yeah? So with the idea that if you are unaware, which probability distribution for the conditional label distribution is the right one, you would spread it over the entire simplex. And if you are quite certain, you would peak the probability distribution at a specific point. Yeah, so the more certain you are, the more peaked you would make this distribution. And yeah, so there are some papers, some works which are doing exactly this kind of predictions, where these hypothesis space, where the hypothesis functions are exactly of this kind. All right, and the question is now, how do you come up with a level 1 prediction or a level 2 prediction? Let's start with this level 1 prediction, and a very common learning paradigm in machine learning. Yeah, so perhaps the very first you learn when you hear a basic machine learning course is the one by empirical risk minimization. And usually you start with the level 0 prediction, but I mean, we can also start right away with the level 1 prediction case. So what do we have there? Yeah, so first of all, we have a hypothesis space, which is, so we call it H1. The indices here will always tell us on which level we are. Yeah, so currently we are on level 1. And this is a subset of all possible hypothesis functions, which are predicting for a feature a label distribution over the labels. Yeah, could be perhaps all possible logistic regressions in logistic regression models for a specific range of the parameters, for instance. And the next ingredient you would need for empirical risk minimization is a loss function, which has the signature it's penalizing a prediction in the form of a level 1 prediction with respect to an observed outcome, an observation on the level 0, if you want. And with these two things, you can specify or define the risk of a hypothesis, which is something like a theoretical benchmark to measure the quality of a hypothesis. And it is given by, well, you simply compute the expected loss of a prediction of a hypothesis H1 of a prediction for the unknown probability distribution P. So P here is the unknown distribution over the X and Y's. And well, if we agree that this is a suitable way to measure the quality of a hypothesis, then we can readily specify what the optimal hypothesis is, namely the one where the risk is minimal. over the specific hypothesis space. And as I said, this risk involves the unknown probability distribution, which we don't know, of course. So what we do in practice is we try to approximate this risk by means of the empirical risk on a data set where we have pairs which are IID samples of the unknown probability distribution. And then the empirical version of this risk is simply the empirical average of the losses evaluated at the pairs. And again, if we have here something like a theoretical measure, which is now also of practical relevance because we can compute it, we can again ask for what is the optimal hypothesis in terms of this measure, and this is then the empirical risk minimizer, so the one with the smallest empirical risk. And under quite mild assumptions, the law of large numbers is telling us, well, the empirical risk converges to the true risk, and so it's quite reasonable to believe that the empirical risk minimizer will also converge to the optimal hypothesis. All right, but then we have to make sure that this optimal hypothesis is reasonable, so that we end up with something which is good for our purposes. And obviously, this is related to the question what a reasonable loss function is in the first place. So because this is essentially what is driving here the behavior of the risk and then consequently of what the optimal hypothesis is. And well, for the level 1 case, so where we are predicting distributions over the labels, and the optimal hypothesis is also nothing else than a prediction mapping feature instances to label distributions, there's a quite obvious way how to answer this question. Namely, it should hold that the optimal hypothesis coincides with the conditional label distribution, because in some sense this is the best you could do. If you would know the distribution, and in particular the conditional label distribution, the best you could do to make the prediction for a given X is to use the conditional label distribution. And for the empirical risk minimization, which you use in order to get a proxy of this optimal hypothesis, this means in particular that your learner who is doing empirical risk minimization has an incentive to learn the correct level 1 uncertainty. So this here is your level 1 uncertainty, the aleatoric uncertainty it's sometimes called. And in some sense, it's the best thing you could do on the level 1. Now the question is, well, is it possible to have such a level 1 loss function? Good news. Yes, there is. So there's a quite heavily studied class of level 1 loss functions which fulfill this requirement, and they are called strictly proper scoring rules. So this is a class of exactly such loss functions where this here holds, where the optimal hypothesis, of course, if the hypothesis class H1 is rich enough, so that the true conditional label distribution is an element of H1, then this is fulfilled. And some examples which are used very often are cross entropy or Breyer score. So cross entropy giving rise to the softmax regression, very often used in neural networks and etc. All right, so we see for level 1 predictions, empirical risk minimization seems to be a good way to go. So we have reasonable level 1 loss functions, and they have the nice property that the learning algorithm, the learner, has an incentive to make faithful level 1 predictions, so to speak. And now what works on level 1 might also work on level 2, you might think. So let's reiterate more or less what we just done, now only one level higher. So you see here now the index is telling us on which level we are. So we are on level 2. So our hypothesis function we are interested in are mapping feature instances to probability distribution over the labels. And we assume that we have a suitable subset of these. So in the classification setting, for instance, you might you can encode this by, or a suitable subset is obtained by looking at Dirichlet distributions where the parameters of the Dirichlet distribution are somehow depending on the instance, on the feature X. And well, what we need next is again a loss function with a different signature. So we have to take into account that we now are doing more complex predictions, in the sense that we have this probability distribution over probability distributions spirit. This is why we changed here the first part of the signature of the loss function. And now again, the question is, what is a reasonable loss function on level 2? And well, we can more or less transfer what we have thought about on the level 1. So first of all, what we would need is we need to have an incentive for correct predictions. Of course, at the end we want to predict and we want to make correct predictions. Plus, because we are interested in uncertainty awareness, and these hypothesis functions here are operating on the level 2, on this epistemic uncertainty, also sometimes called. We want that the level 2 uncertainty, that this is reported in a faithful manner if we do empirical risk minimization with this loss function. All right, and there are a couple of suggestions how to come up with a reasonable level 2 loss function, and most of them have the following form. So the level 2 loss function for a given level 2 hypothesis H2, evaluated at X, and with respect to some label Y, is given by the expected level 1 loss if we would draw a level 1 distribution according to this level 2 distribution H2. This is what we do here. So remember, the H2 is a level 2 distribution. So it's a distribution over distribution. So you can here more or less sample a distribution from this level 2 distribution, and then evaluate it on a level 1 loss function, where the signature is that you here have in the first argument a level 1 prediction. And because this here is sometimes too overconfident, in the sense that it's incentivizing to making two peak distributions, what is oftentimes introduced is a penalty term, or a regularization term, where deviations from the uniform distribution over the entire simplex, over the entire probability distribution space of the labels, is penalized. So here KL, this is the KL divergence, so nothing else than a distance measure for probability distributions. And what we compare here is the level 2 distribution, which we use for prediction, and we compare it with the uniform distribution. Yeah, so if we deviate from a uniform distribution, yeah, so we give every probability distribution in the simplex the same mass, then this penalty term will be high, and this is steered by this lambda here. And the idea is to avoid overconfidence, which will be the case if we just look at the first component here, now only this averaging level 1 loss part here. All right, so these are the existing, or the class of level 2 loss functions which were considered in the literature so far. And now the question is, well, are they really reasonable? Yeah? So is it really the case that these losses here are doing these two things in a appropriate way? And well, so first of all, we need to somehow specify what reasonable is, yeah, to grab it mathematically. Yeah? So we are here interested in the theoretical and the fundamental properties of these level 2 loss functions here. And so our suggestion in the paper was to formulate these two requirements, these reasonable requirements as follows. So we say that the empirical risk minimizer for a level 2 loss function L2 for the given data should fulfill, first of all, the requirement that the more data we get, the smaller in expectation should be the level 2 uncertainty, which makes sense. The more data you obtain, the more X and Y pairs you have, the more you are certain what the underlying conditional label distribution is. So from a picture point of view, you start with, if you have only few data, you have a quite, not concentrated level 2 distribution, and the more data you get, the more concentrated it is. So this is the first requirement which should hold, arguably. The second one makes sure that if you have infinite data, so imagine the case that you would have here an infinite amount of data points, of data pairs X, Y, and Y, I, then the empirical risk minimizer should concentrate around the correct distribution. And what is the correct distribution? Well, it's the conditional label distribution in this case. So we make sure that the uncertainty decreases the more data we have, and that we have a tendency to make correct predictions. So this is essentially what requirement R2 is telling us here. So quite high level assumptions. We can argue about that, whether they are reasonable or not, but we believe that these are two very basic requirements which should be fulfilled for an empirical or suitable empirical risk minimizer based on a suitable or a reasonable level 2 loss function.
Might I have a question?
Yeah, sure.
That's fine. Yes, I was wondering, so here when you mean infinite data, is it could be that also the XY pairs that are infinite, right, for training, that also the inputs X are different, so to say. So maybe I will just try to clarify. So let's say we have like infinitely many different training data, but these X's are very different from the X's that we observe at testing time, so to say.
Okay. Yeah. What we look at here is, let's say, the very classical machine learning scenario where your training data is generated by some fixed but unknown data distribution, P, and at testing time you observe again, or you would observe X's where the distribution is unchanged, so to speak.
Okay.
So you don't have a shift or something like that.
Thanks. Okay.
All right. And well, so what we then have shown in our paper is the following, namely that these this class of level 2 loss functions, where you have this averaging of level 1 losses plus penalization, this KL divergence penalization, that they are in general not fulfilling these two requirements. If you use commonly used level 1 losses for the averaging part here. So the reason is that you have either the first requirement violated or the second one. So this is quite general what we have shown. So I want to show you exactly what the results look like. So this is the high level summary, more or less, of the results, and now comes the more micro level summary of the results. What we considered in the paper was, for simplicity reasons, the case where we have learning without features, more or less. So the feature space consists of only one meaningless feature. But I have to tell that these results which we see here are, it's straightforward to extend them also for the case where we learn with features. It's only a bit easier to write them down, so that we don't have to condition on the X and such things. And our theoretical result is essentially as follows. So in the one case, so we have a level 1 loss function, which we use for averaging, in this level 2 loss, in this class of level 2 losses. And all we need to require is that this level 1 loss function is strictly convex in its first argument. And then what we can show, which we can prove, is there is some lambda bar, such that for any lambda smaller than this lambda bar, the first requirement is violated. So in the sense that your uncertainty does not decrease in expectation if you obtain more and more data. The reason is more or less that it's quite easy to understand. So if you penalize too low, more or less, you have an overconfidence. So your level 2 prediction will be too peaked, and it will be peaked such that the uncertainty cannot decrease more or less anymore. Now the second case, so again, we are still interested in the level 1 loss functions. And if the level 1 loss functions are such that they are strictly proper, so these reasonable level 1 loss functions we had for making level 1 predictions. And it is additionally locally Lipschitz in the first argument. So it's a technical requirement, but it's commonly fulfilled for level 1 loss functions. And then we have the more or less opposite case, namely that we have now a lambda underlined, such that if we use a lambda which is greater than the lambda underlined, yeah, then the other requirement is violated, yeah, so that we don't converge to the true conditional label distribution. Yeah, and again here this makes sense, because if you penalize too much, you will lose the property to converge to the right thing. Yeah, so you will have an incentive, or the level 2 empirical risk minimizer will have an incentive to be more non-peaked than it should. No? We'll never concentrate around a single distribution, more or less. And well, question is, are these two properties fulfilled now on the level 1 loss function? For example, Breyer score and cross entropy, now both commonly used in these scenarios. They both are strictly convex, and also both are strictly proper and locally Lipschitz in the first argument. Yeah, so initializing these level 2 losses with the Breyer score and cross entropy will end up within this theory, the scope of this theory. All right. We also considered a couple of empirical things in our paper. So as a reminder, yeah, these are the loss functions we are interested in. And to show you what we have done, we considered for the level 1 loss the Breyer score. We used for the hypothesis space, yeah, which we need for empirical risk minimization. We used here a 2-component mixture of Dirichlet distribution, so that we have also the case where we have bimodal level 2 distributions, yeah? Not only unimodal, which would be the case if we just consider Dirichlet distributions. We considered a high aleatoric uncertainty case, yeah, so a high level 1 uncertainty scenario, in the sense that in our data distribution, yeah, py given x is the Bernoulli distribution with success probability 1/2. Yeah, so we considered a quite simple binary classification setting. Yeah, so where we only have 2 classes, and the highest aleatoric case is in this scenario if you have a fair coin. Yeah, so you don't can tell which class it will be so easily. Yeah, and what we then reported was what the empirical risk minimizer will look like in terms of its mean entropy, where we quantized this entropy. So a Dirichlet distribution is a continuous distribution, so it has a differential entropy, which is a bit different than the Shannon entropy for discrete distributions. But what you can do is you can, of course, discretize your distribution, compute the Shannon entropy of this discretized version. And this is, if you do a simple correction, an estimation for the differential entropy. Long story short, this mean entropy quantized version is a bit nicer to interpret regarding the peakness or non-peakness of the Dirichlet distribution, or the mixture of Dirichlet distribution, in the sense that if you have an entropy of 0, it's more or less a point mass, and the higher it is, the more it's looking like a uniform distribution. All right, and we considered 5 scenarios where we have 5 different sizes, or 5 different flips of this fair coin, more or less. We started with the case where we do not penalize at all, and well, not surprising at all, the mean entropy is 0 throughout the time. Yeah, so the empirical risk minimizer over the different runs has always a mean entropy of 0. Yeah, so it's a point mass in every case. This is also the case if we make the penalization a bit larger. If we make it even large enough, then what happens is that the mean entropy is changing quite drastically. Yeah? So because then this penalty term here is more or less active. Yeah? So it's active in the sense that the empirical risk minimizer avoids to make a two-peaked distribution, yeah? To have a point mass distribution. And you see, okay, it seems like the decreasing behavior is indeed given. Yeah? So the higher your data set size, yeah, the smaller the epistemic uncertainty, yeah, the more peaked your level 2 distribution. This is also the case for even higher lambdas. Yeah? So here 0.5 and also other ones. All right, you might say, well, looks like good results, but the problem is we have here 100,000 coin flips, yeah, of a fair coin, and still the entropy, this mean entropy is non-zero. Yeah, after 100,000 coin flips, yeah, so there's no x involved, only the y's. To make a comparison with what the empirical mean would be, yeah, for making so the empirical mean of this coin flip in all of these examples. So after 100,000 coin flips, we are perfectly estimating 0.5 with a very low standard deviation. Yeah? So it's a bit questionable why the entropy is that high. Again, the reason is that the second requirement is not fulfilled for such a case. Yeah? If you make the lambda too high, you won't converge more or less to the point mass on the conditional label distribution. Now the question arises whether this is perhaps specific to this scenario where we have the high aleatoric uncertainty or the highest aleatoric uncertainty case in the two-class in the binary classification setting, but the answer is no. So we see the same effect if we now have a very low aleatoric uncertainty. So we have here a very low success probability. So we will see a lot of zeros in our observations, and the picture is essentially the same, yeah, for the empirical risk minimizer. All right, so
I have maybe another question. So
yeah, sure.
You mentioned this lambda bar and lambda underbar, so to say.
Yeah.
So here, could it be that lambda underbar is below lambda bar, and there is some small range, maybe between 10 to the power of -5 and 10 to the power of -1, which is like a good one?
This could be the case. This is this is a good question. I mean, if we look at the theorem, what we were not able to show was to show that this lambda bar and this underlined lambda, that they are coinciding more or less. Yeah. So once you make the lambda smaller than the lambda bar, you are violating R1, and once you are higher than this lambda bar, then you are violating R2. So it might be indeed the case that there is a range somewhere in between. We haven't, I mean, I just used here a couple of lambdas and to simply show the, or to confirm the theoretical results rather, yeah. But of course, it might be the case that there is somewhere a lambda in between these two, where things are going correctly, but this is something which needs to be investigated more thoroughly.
Makes sense. So I guess even like empirically, did you check, maybe because it's hard to prove theoretically, but just empirically, just observing like really in much details this specific range between 10 minus 5 and 10 minus 1?
Yeah. But what is interesting about the result is that you can switch from one regime to the other, yeah, quite drastically. I mean, here you have for all the dataset sizes essentially no epistemic uncertainty reported, and then you jump right into reporting level 2 uncertainty, epistemic uncertainty right away. Yeah, so for practical cases, perhaps there's much to do for finding out the correct lambda, more or less.
Makes sense. Yeah, thanks a lot.
Yeah, thanks for the question.
I also have a question.
Yeah, sure.
In the loss L2, like the first summand, is it somehow weighted with the number of training data points? I'm not sure how to interpret this expectation, or like
No, this is really the loss function, how it is specified. Yeah, so this is how your H2 is a level 2 distribution, and here you would essentially draw distributions, level 1 distributions, according to this level 2 distribution, and then compute the average level 1 loss. For the empirical
but wouldn't it maybe make more sense if one would weight it with the number of training data points, that if you observe more training data points, that this should be more, I think then you would have also this R2, that then if you have 10,000 training data points and you multiply the first summand by 10,000, then it would be more concentrated about the true solution.
Yeah, but what is the true solution?
I mean, it would be more, what you want, that the more data points you get, the more it concentrates until the level 2 uncertainty vanishes. I think one would get this if you multiply the first summand by the number of training data points.
I'm not so sure whether this will be the case, to be honest. I mean, first of all, so what is a loss function? So a loss function is, a theoretical function which is, first of all, not depending on the size at all. Yeah. So think of cross entropy, Breyer score, 0-1 loss functions. Yeah, there is never in the definition something involved with the sample size, right?
Yeah, I mean, it depends. Like in our papers, we usually in the empirical loss you divide by the number of n, and we don't divide by number n. Then it's more, from a Bayesian perspective, then it's more like a likelihood, where the more training data points you observe, the more emphasis is on the likelihood, and you have less emphasis on the prior. If you see it a bit Bayesian, that the second term is something like the prior, which is quite uniform, and the first term is more the data term. And if you observe more data, then the data term should be more emphasized, and if you observe less data, then the prior should be more emphasized, I think.
But this is what was happening then in the empirical risk, right? So the empirical risk, if you remember, so in this case it would be 1 over n if your number.
Yeah.
This would then of
Yeah, and I
course
think
look
it's
like
this
this.
1 over n, and the empirical risk is the problem. If you would leave it away, it would, you would get you would get, if you leave the 1 over n away, you would get an algorithm which fulfills that the epistemic uncertainty vanishes in the limit.
No, why should it? I mean, it doesn't matter whether I maximize R2H2 or I multiply it
Because,
with.
yeah, I mean, this would make no difference, but if you keep the lambda from the second part the same,
Yeah. But then again, so you
okay,
just
I mean,
you
then it
just
would
you
need to
should
be
you just shift
outside of.
yeah. You just shift the range of the lambda more or less then.
Okay, or I think another point of view would be that you decrease if you would decrease the lambda with n, with growing, if you divide the lambda by n, or if you multiply the loss by n, if you would do one of these things, then the epistemic uncertainty would vanish, I think.
Exactly. So this is perhaps one fix. If you make the lambda, yeah, so here the problem is essentially that the lambda is always fixed. Yeah, so it's a fixed lambda.
Yeah.
And what these paper are also doing more or less, yeah, they are implicitly making the lambda depending on the sample size. But if you would use a fixed lambda, now this is what you see here, then the problem arises as mentioned here. But yes, so if you would consider a lambda depending on the n, on the sample
and
size.
equivalently, you can also keep the lambda fixed, but leave the 1 over n in the empirical loss. That's equivalent if you just multiply if you put the lambda in the other term, but
Yeah, okay. Yeah.
Okay, yeah.
That's true.
But then in this case, so if the lambda decreases with the number of the data points, then with like more data, then it will be super small. Then this will be like will violate one of this part of the theory, because if the lambda is too small, then it will be consistent, but it will not be suitably confident. It will be
okay. Maybe we can talk about it afterwards.
Yeah, kind of.
Okay, but thank you.
I mean, as far as I understood, what you are essentially suggesting is to have a loss function which is more or less having a third component, more or less. Yeah, so it's also allowing to have a third component which depends on the sample size you observed, right?
Yeah, I would just multiply the first summand by capital N by the number of training data points.
Yeah.
But or equivalently divide lambda by capital N.
Yeah. But then, of course, you have to do the theoretical analysis once again. Yeah. So the results we have here, they are exactly for this case. Yeah. For lambda fixed, loss function is not depending on the sample size, of course.
Okay.
And this is obviously somehow the drawback of this approach. Which we also criticize more or less here.
Yeah, I totally agree. It's just this would be kind of a fix to get another loss where it would work better effectively. Thank you.
All right. Good. Then let me jump quickly to the conclusion. So what we saw is, well, these level 2 loss functions, not in general appropriate because you either have these overconfidence or the no consistency of the empirical risk minimizer. But although we criticize these level 2 loss functions, one has to say that they are still helpful, especially for out of distribution tasks. So where you want to show that, well, now we have an instance which is out of distribution. We haven't seen something like this during training. So now the uncertainty, the epistemic uncertainty is quite high. But still, it's rather something like a heuristic. As we pointed out that the theoretical properties of these things are quite questionable regarding the faithfulness of this representation. There are also similar issues in regression. So we just considered here classification, but for regression, there is this approach, deep evidential regression, where something similar happens. And of course, then the question arises whether we can construct a level 2 loss function at all, which is incentivizing faithful level 2 uncertainty representations. And we have a follow-up paper on that where, well, we show that it seems like having such a faithful representation by means of an empirical risk minimizer is very difficult to observe or to obtain. We have considered here both cases, the classification and the regression, but our definition of reasonableness, these two requirements we saw a couple of slides before, is a bit different. So here what we did in this follow-up work is we considered these scoring rules and asked whether there is something like a second order scoring rule for these level 2 distributions by making use of characterizations of these scoring rules, more or less. And then we saw, well, the class of level 2 loss functions where you don't have a scoring rule, a proper scoring rule, is even larger than the class of level 2 loss functions we have considered here. So these averaging level 1 losses plus penalization, the divergence penalization. All right, so this is it for what I wanted to share with you. So thank you for your attention, and here are my references.
Thanks a lot. Thanks a lot for the great talk. I would have some questions, but maybe some other people would like to start. I can just start with one question. So here you mentioned that this paper focuses on classification, right? But there is the other paper on the question. So maybe one other question is, so here there is usually we have some models which generate this hypothesis H1 and H2, I guess. I was wondering if there are some characteristics of the models that could give better properties in the results that you show here, so to say.
Okay, so your question is whether you can somehow restrict the hypothesis space so that you can. That's a good question, because perhaps this is also important to mention. These theorems here, they are also looking at the case that we can. So our hypothesis space is rich enough that we can more or less we can have these point masses on the level 2, and more or less. Oh, okay, no, not really. So it's enough to have the point masses and also the uniform distributions, more or less, and a bit in between. Yeah. But you were asking whether you can even restrict it more, so that you cannot come up with such properties, right?
So
with these negative properties.
I feel that since this theorem do not do any assumptions on how H1 and H2 are generated, I guess it should probably hold even if we restrict even more like the hypothesis space, right? But I was wondering if there are maybe some ways to avoid a bit, like which gives slightly better properties, some way to restrict a bit more to avoid some of this bad effect.
Yeah.
It's quite, I don't know, general question and maybe hard to answer, but just, I don't know, if you have some thoughts.
Yeah. So, I mean, once your hypothesis space has these point masses, yeah, so where you have full certainty representation and uniform distributions on the label on the level 1 label distributions. As long as you have these two cases, and I mean, this is not much. This is, I mean, essentially every reasonable hypothesis space should include exactly these two cases. Yeah, so we have this full certainty and full uncertainty, both on epistemic level. As soon as you have these two, then it breaks down.
Okay, makes sense. Yeah, thanks. Okay. Maybe, okay. I have a second question, if that's fine. So the second question is, at some point you mentioned this ground truth aleatoric uncertainty.
Yeah.
I recall at some point that we discussed that is there any ground truth epistemic uncertainty? So I was wondering if you have any new insights on this.
Yeah. I mean, for the aleatoric uncertainty, given this machine learning perspective that your data is generated by some unknown probability distribution, then there's obviously this objective ground truth of aleatoric uncertainty. For epistemic uncertainty, it's it's the question: what is the ground truth as an objective ground truth level 2 or epistemic uncertainty representation? And I think there is nothing like an objective. So there's always a subjective one. I mean, you can also transfer this to the real life, more or less. So what is the true representation of your lack of knowledge? Is there something like this? It seems like this is always subjective, not objective. What your lack of knowledge representation should look like. And this is right now my my point of view on this.
Makes sense. I was also asking because of this follow-up work where you define this second order proper scoring rule. So I was wondering if here you define this ground truth epistemic uncertainty, or it's also agnostic. It's different thing.
This is interesting that you ask. So what we do here is so the negative results we show here in this paper are like, pretend there would be something like a subjective ground truth distribution, level 2. Then we ask the question, given this fact, is there a level 2 loss function which would recreate or recover exactly this level 2 distribution? And what we show is, in general, no. Again, you have either the tendency to pretend more certainty than the ground truth would allow, or the other way around, yeah, that you pretend too much uncertainty.
Okay. Okay, makes sense. Yeah, thanks a lot for the answers.
Yeah, thanks for the interesting questions.
Yes, Jakob, I'm not sure if you have any question.
Yeah, for this question here in the last slide, if there's an appropriate level 2 loss function, I think with the scaling of the n in the regression case, I think in our paper we have proven at least that it fulfills the second property. That so if you multiply the first term by n, and then that in the limit theta to infinity the uncertainty vanishes. So yeah. Or maybe I understood something wrong, but or do you have an intuition where you can directly say that this is not true? Or for me, because I think this kind of solves this problem that if you multiply the first term by the number of data points, that then you have both these properties, R1 and R2.
So of a different kind is here meant to, you still have the classical signature of a loss function. Yeah, so you compare prediction with observation.
Yeah.
This is the question aiming at. Yeah? So if you have such a loss function of that kind, is there another way to specify it such that you have faithful uncertainty representation? But what you are, or at least as far as I understood, you were suggesting a non-traditional level 2 loss function where you have the signature prediction, observation, and dataset size. So you have 3 inputs, right?
Yeah.
But this is then a different way how to interpret different
how
kind.
to frame the whole problem.
Yeah, exactly. And this seems to be the right way to go, more or less. Yeah. So traditional level 2 loss functions, yeah, with this prediction compared with observation, this is obviously a fundamental problem, yeah, to make faithful uncertainty representation.
Yeah, I think it kind of needs the number of training data points to know how sure it can be.
Exactly.
Yeah.
Great. Do you have any other questions also, Jakob? Or
yeah, thank you. It was a very nice talk.
Great. Then thanks again, Viktor, for presenting your paper. That was really interesting. We'll just stop the recording